So thanks for the invitation. I am Akash. Currently, I am a faculty member in IIT Patna in the Department of Physics. Today, I am going to discuss about charge state tunable magnetism in manganese doped 2D transition metal dichalcogenides. So the topic is very specific, but I will discuss in broad manner, like what are point defects, how does they form in a crystal system, and why the study of point defects and impurities are important in solids. So to begin with, let's see how the point defects form in a crystal system. So during the synthesis of a crystal system, at the growth temperature, thermal energy is enough to break the bond and create a vacancy, and that vacant atom can go somewhere else inside the crystal system and it can stabilize as an interstitial atom. It might also possible that cation and anion can switch their position in the system, and by that time your defect is known as anti-site of defect. It might also possible that from the precursor some foreign atom can take the place of latticite, and that is known as substitutional atoms. For example, this is the growth of 2D WS2. So intrinsically, you will have sulfur vacancy on top and bottom, and it might also possible that you will have chromium substitution at the tungsten side and molybdenum substitution at the tungsten side. So this is how defect formation happens in the solid. Now, why the study of point defects are very important? Basically, they can design the electronic and optoelectronic devices. They can control the p-type and n-type conductivity of a given semiconductor material through providing several states. For example, in gallium nitride, which is a very popular semiconducting material, when magnesium will take the place of gallium site in gallium nitride, it will provide a shallow acceptor level near to the valence band maxima. So that's how you can get the p-type conductivity in gallium nitride. And using this p-doped gallium nitride, Suji Nakamura and their team, they developed the blue LED. By using red, green and blue LED, we can get the white LED, for which they got Nobel Prize in 2014. Moreover, defect can induce the magnetism, and recently it has been found that the deep level defects, those are considered to be the trap center and they can degrade the device performance. Those are actually very useful, because if defects, if the deep level defects will have deep level defects in the semiconducting material, and by engineering of those defects, if we can tune if we can form two-level system within the band gap, then it can be the source of single photon emission in a semiconducting material. For example, in HBN, when boron vacancy will be there, then it will form two-level system in the gap of HBN, which is a very wide band gap semiconductor, and through which we can get the single photon emission. And that has a direct application in quantum sensing, communication and computing. So in today's talk, I mainly discuss about how the defect can control the electrical conductivity of a material, how we can tune the deep level defects to shallow level, and how defect can induce the magnetism in solid. Okay. To discuss those details, first we need to have a standard notation, how to read the transitional level plot, how to analyze the defect analysis through the first principle approach. So let's see how we can calculate the formation energy of a defect in charge state Q. So in first principle approach, we always, for defect calculation, we follow the supercell approach when we'll have a large system where we'll dope or we'll create the defects. So here, this is the total relaxed energy of a defected system in charge state Q, and this is the total relaxed energy of a system, defect-free system. Ni is the number of elements which we are going to dope in the bulk system to create a defect, and mu I is the chemical potential of that species that we are going to add or remove from the bulk system. So far your defect is neutral, but generally or most of the time defect is charged. I mean, it will provide several states within the band gap, and depending upon the Fermi level position, it can be acceptor, donor, deep acceptor, shallow acceptor, many more. So accordingly, we have to consider that energy also. I mean, that's how we can analyze the defects. So Q is your charge state, and EF is the Fermi level position with respect to the valence band maxima. And then since we are modeling the defect, so there will be a periodic boundary condition. It might possible that defect can interact with its periodic image. So we have to consider that interaction also to get the isolated defect formation energy. For example, this is the growth of zinc oxide in oxygen poor condition and oxygen rich condition. And if we'll take the example of, let's say, oxygen vacancy, so you can see that in oxygen poor condition, oxygen vacancy has the less formation energy compared to the oxygen rich condition, because in oxygen rich condition your oxygen interstitial is the lowest in formation energy, and that's how the concentration of oxygen interstitial will be higher in oxygen rich condition compared to the oxygen poor condition. And this is the thermodynamic charge transition level, where y-axis is the formation energy and this one is the valence band maxima. This is the conduction band minima. This is the band gap of that semiconductor material where we are going to study the defects. Sorry. Depending upon the defects, we can have a positive slope that will indicate your donor defect. You can have a negative slope that will give you acceptor defect, and you can have a straight line that is electrically inactive defect. The same defect can behave as a donor defect till this Fermi level. Same defect can be electrically neutral for this range of Fermi level, and same defect can behave as an acceptor defect for this range of Fermi level. And depending upon these kinks, this transition, they can be deep or shallow. So if these the excitation energy is just few millielectron volt, then you can say these are the shallow acceptor or shallow donor. Otherwise, they are deep. So, for example, for this material, it is very hard to dope a p-type, because you can see that thermodynamically donor defect is much more stable compared to the acceptor one. And for this one, you can tune the electrical conductivity by tuning the Fermi level. And again, for such type of material, it is very hard to dope n-type, because p-type is thermodynamically much more stable compared to the n-type. Okay. So now I will discuss about the electrical conductivity, how defect can control the electrical conductivity with the example. So as grown monolayer MOS2 is an n-type semiconductor, and it has been observed that during the synthesis of monolayer MOS2, you can have sulfur mono vacancy, di vacancy, some anti-sites of defects, then some complex of vacancy. And if we'll compare the concentration of all these defects, you will find that sulfur mono vacancy occurs more compared to the other defects. So anyone can guess, or anyone will predict that since sulfur mono vacancy is higher in concentration, so this will be the reason for its unintentional n-type of doping. But if we'll look at the electronic picture of all these defects, especially for the sulfur vacancy, you can see that sulfur vacancy is providing several trap states near to the conduction band minima. So it has tendency to trap the mobile carrier rather than providing the free carrier. So it cannot be the source of free electron. So it cannot be the source of n-type conductivity of a monolayer. Also, for di vacancy, it is almost similar. Again, you will have a trap state. And for this anti-site of defect, when two sulfur is replacing one single moly, so you will have a donor level definitely, but it is again far below from the conduction band minima of the order of, I guess, 1 electron volt. So again, this is a very deep donor. So you can say that these defects are not the source of its unintentional n-type of conductivity. Then what is the reason for n-type of conductivity of this monolayer MOS2? So with this challenge, we tried to address this problem with the first principle approach. So first, we optimize the geometry definitely we took a larger supercell, maybe 10 cross 10 cross 1, and then we considered the sulfur monovacancy, all the observed defects, we optimized, and then we did the thermodynamic analysis of all those defects. So here you can see that till this Fermi level, from here, from valence band maxima to here, the sulfur monovacancy has nature to stabilize itself in electrically inactive form. It is stable in neutral charge state. It cannot accept or not donate any electron. I mean, it cannot accept or give the electron to the system. So it is stable in electrically neutral form. But when your Fermi level is near to the conduction band minima that you can do to the gate voltage, then you will find that it is stable in negative slope. That means it has tendency to accept one electron rather than providing the free carrier. So again, this thermodynamic analysis can predict that sulfur monovacancy has tendency to accept the electron rather than providing the free electron. And sulfur divacancy will follow the same trend, and you can say that sulfur is always accepting the electron, and thermodynamically it is a very deep acceptor defect in monolayer MOS2. And other defects are already, I mean, they are complex. All of them are amphoteric. Sometimes they will provide very deep donors, sometimes they will provide very deep acceptor. So in conclusion, you can say that all these experimentally observed defects are not the source of n-type conductivity of monolayer MOS2. Then we followed the experimental way how we can grow the single layer MOS2. So these are the literatures. They suggest that the source of sulfur they have considered is H2S gas, through which we can grow the single crystal of molar MOS2 for the larger scale. Okay, and also they have suggested that during the synthesis of this MOS2, you will have several hydrogen impurities will be there, sulfur monovacancy, divacancy, or some complex vacancy will be there. Okay, so following this experimental suggestion, next we did the analysis, thermodynamic analysis, defect thermodynamic analysis of this defect. We found that structurally hydrogen will be stable in two forms. One is hydrogen interstitial, when it will go inside the hexagon center, and second is hydrogen will stabilize itself on the top of sulfur atom. So this is hydrogen HS add atom, and you can see that for the entire range of Fermi level, this hydrogen interstitial is stable in +1 charge state. That means it has tendency to donate one electron. Doesn't matter your Fermi level is here or here or here. So for the entire range of Fermi level, it will be always ionized in +1 charge state. And this hydrogen add atom will provide an effective donor level, shallow donor level near to the conduction band minima, which is almost, I guess, 0.2 electron volt. Okay. But the interesting part is this one. When your MOS2 is grown in S-rich condition, then thermodynamically your hydrogen impurities will be much more stable compared to the mono and di sulfur vacancy. But in MO-rich condition, when your sample is grown in MO-rich condition, then you will find that thermodynamically your sulfur mono vacancy is much more stable for this range of Fermi level. So hydrogen will lead the n-type conductivity in monolayer MOS2 when the sample is grown in S-rich condition, because by that time thermodynamically hydrogen impurities will be much more stable compared to the mono and di sulfur vacancy. And on the other hand, for MO-rich condition, your Fermi level pinning will be there. There will be competition between this positive slope and this negative slope, and that's how your Fermi level will be forced and fixed to this 0.48 electron volt below to the conduction minima. Okay. Next, we did the electronic density of state analysis and migration barrier height. And they are in the electronic density of state analysis, you can say that hydrogen is providing effective donor level inside the conduction band, and high migration barrier height is ensuring that they will be always ionized, as well as they will be stable as it is in the sample. So the growth temperature is, if I am correct, it is 1200 Kelvin, right? So by that time also this defect will not able to migrate over the lattice, they will be stable as it is, as they are in the crystal. So this was all about controlling the electrical conductivity of a semiconducting material. Now let's see how we can tune the deep level defects to shallow level through the hydrostructuring. So in the semiconducting physics, suppressing the deep level defects are always challenging. Once the defect is created, the associated defect transition levels are fixed, and without altering the integrity of material, you cannot tune the deep level defects to shallow level. Okay, but people have tried to tune these deep level defects to shallow level through substrate engineering or alloy engineering, but they are fine, but they are not that much significant so that we can use in the device performance. And recently it has been proposed that van der Waals heterostructuring of 2D material can be a promising approach through which we can tune the deep level defects to shallow levels. So in this work, we have tried to tune the deep level defects, that is providing through the molybdenum vacancy in MOS2 through the van der Waals heterostructuring of WS2. So directly I will show the result. So in single layer MOS2, molybdenum vacancy will provide several mid-gap states within the band gap. These are the donor levels, doubly degenerate donor levels, and these are the acceptor levels. And they are, since this donor level is far away from the conduction minima, so this is very deep, and these are the acceptor level, again they are very far away from the valence band maxima, so they are again very deep. Following the same trend, you will have a trap states within the band gap of tungsten defected WS2. Now, when we will put WS2 layer on the top of moly defected MOS2 or MOS2 layer on the top of tungsten defected WS2, you will find that through the band renormalization, your valence band maxima is shifting up, and those defects which were very deep in monolayer counterpart, they are going to be shallow in van der Waals heterostructure case. So here, this is just a few millielectron volt with respect to the valence band maxima for this heterostructure, and again for this case, it is of the order of maybe 0.5 electron volt. So that's how you can say that van der Waals heterostructuring of 2D material can tune the deep level defect to shallow level. Okay, next, if we'll compare, you will find that the transition level of 0 to -1 in MOS2 it was 1.16 and 1.02. This is the 0 to -1 transition from molybdenum vacancy from MOS2 and WS2, and when we'll put the layer depending upon the MOS2 on the top of WS2 and then WS2 on the top of MOS2. Then you will find that this was earlier here, in heterostructure it is here. So it is 4 times shallower, and this is again 2 times shallower. So it is again ensuring that van der Waals heterostructuring of 2D material can tune the deep level defect to shallow levels. Okay. So, so far we discussed about controlling the electrical conductivity of a material through defects and how we can suppress the deep level defects to shallow level through the van der Waals heterostructuring. Now I am going to discuss about defect induced magnetism, how we can induce the magnetism through the defects. So recently it has been suggested that dilute magnetic semiconductors are the promising for the spintronic applications, and people have already synthesized chromium iodide, which has the Curie temperature. But yeah, it is struggling with the Curie temperature and high magnetic anisotropy, but again it is a magnetic semiconductor. So the problem is still there to get the high magnetic anisotropy as well as the high Curie temperature, so that we can use at the room temperature. So here in this work we have tried to dope MOS2 and WS2 with experimentally suggested magnetic impurities such as manganese in cluster form, as well as manganese doping interstitial and many more. So again, using the manganese impurities in MOS2 and WS2, we are going to make it dilute magnetic semiconductor, and we'll see that how much Curie temperature or magnetic anisotropy is there. So first, this is the, again, we following the supercell approach, this is the relaxed structure of all those suggested defects, and these are the electronic density of state, which are ensuring that all these defects are providing magnetic moment. So all these defects are magnetic. For example, when manganese will replace one sulfur, then it is providing 3 mu B as a magnetic moment, then 7 mu b, and then 4 mu b and 1 mu b. And especially for the manganese top, when manganese will stabilize itself on the top of two surrounding selenium sulfur atom, then it will push the Fermi level near to the conduction band minima, and it is transferring the semiconducting behavior of this MOS2 to the, I will not say metallic behavior, but it is pushing the Fermi level from below, from mid of the gap to the conduction band minima. Okay. Next, this is the molecular orbital picture for MOS2, 2D MOS2 and WS2, and here, depending upon the overlapping of orbitals, you can have bonding orbitals and anti-bonding orbitals, and sometimes you will have non-bonding orbitals. And you will find that highest occupied orbital is your in anti-bonding orbitals, which is coming from the A dash. And again, the orbital character will be, I think it will be tungsten tungsten d orbital and MO d orbital with less contribution of chalcogen p orbital. And this is the crystal field splitting and Hund exchange splitting of all those defects that we have considered, and these are the spin density of all those things. So we can see that for this case, your single Mn is surrounded by 3 MO atom. So they will be anti-ferromagnetically coupled to each other, but resulting they are providing a magnetic moment. Okay, and again, depending upon the orbital interaction, you can have a crystal field splitting something, and you will have exchange splitting. Okay, and then we did the thermodynamic analysis of manganese clusters, Mn clusters. So we considered in the modeling when both of the Mn will provide single electron in paired up, then they are ferromagnetically coupled, and if they are up and down, then you can consider as an antiferromagnetic. So here thermodynamic analysis suggests that when your system is grown in amorous condition, then this defect is much more stable than the pair, the manganese clusters. And also interestingly, you can see that when your system is n-doped, thermodynamically ferromagnetic coupling is much more, this dash line is much, it is much more stable compared to the AFM, antiferromagnetic coupling. So you can say that since intrinsically your MOS2 is an n-type semiconductor, and when these magnetic impurities will be there, then ferromagnetic coupling will be more compared to the antiferromagnetic coupling. Okay, but in S-rich condition, you will find that this case, when a single Mn will replace a molybdenum, it will have a higher formation energy, so it will not be thermodynamically much more stable. But if we'll compare this one, because all these numbers are in minus, so their concentration will always be there. Okay. So this was for the MOS2, and for WS2, unlike to the MOS2, you will have an amphoteric behavior. The same defect will we have as the donor one, then electrically neutral, and then the acceptor one. And from the magnetism point of view, it will be stable in antiferromagnetic with very less energy difference between ferro and antiferro. It will be AFM, till here it will be antiferromagnetism, but in neutral charge state, again it will be stable in ferromagnetism, but again for the negative charge state, it will again be stable in the ferromagnetic. So you will have an alternate character of magnetic behavior. Now, following this literature survey, because once magnetic impurities are there, their character will be fixed, whether they are ferromagnetic or they are antiferromagnetic. You cannot tune. Definitely you can modify or engineer with the electrostatic doping or strain engineering or hydrostatic pressure and blah 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 many things. But here I am following this literature survey, which are suggesting that through the electrostatic doping, when you will provide extra carrier within the band gap, those extra carrier will interact with the double pair up and up down channel, and that's how you can modify or alter the magnetism. So following this one, we doped through the electron I mean, we wrote the system through the electron and hole doping, and we found that you will have a you can engineer the magnetism, like for till this concentration of manganese, you will have a ferromagnetic coupling. For this range, again, you will have up and down. So all I'm saying that through the doping of carrying concentration, you can tune the magnetism in solids, basically in 2D TMTs. And you can say that in MOS2, this is the stable structure till here. Till here, your AFM, anti-ferromagnetic coupling will be there, and after that, ferromagnetic coupling will be there. For WS2, anti-ferromagnetism, ferromagnetism, and again anti-ferromagnetism. Okay, so recently we did the magnetic anisotropy. Just to it. Recently we did the magnetic anisotropy analysis, and we found that in 2D MOC2 and WS2, you will have very high magnetic anisotropy, which is ensuring that it will be stable, and the thermal fluctuation will be very less. And we calculate the Curie temperature for 2D MOS2 and WS2 for the same manganese impurities, and the TC is around more than 300 Kelvin. And since in WSE2, anti-ferromagnetic coupling is much more favorable, that's how we calculated the Néel temperature, and this is the Néel temperature. Okay, so in conclusion, defects can control the electrical conductivity. We can tune the deep level defect to shallow level through the van der Waals structuring, and definitely you can, through the carrier doping, you can engineer the magnetism in 2D materials. And with this, I would like to acknowledge my professor, my PhD supervisor, Abhishek Singh, then Vivek Shanai, Neha Narang, and my PhD student. Thank you. That's it.
Thank you. Questions?
Yeah, I guess nice talk. So one thing you told that the sulfur plus hydrogen combination giving the N-type characteristics to molybdenum sulfide, right?
Actually, it is hydrogen interstitial.
How the coordination occurs? How is it the special coordination of a hydrogen? How it is? Suppose they have a trigonal prismatic structure. Where is the position of the hydrogen?
Yeah, that's what I'm saying, that it will stabilize in the center of the hexagon. It will stabilize in the center of the hexagon. It will be hydrogen interstitial. And the second one is on the top of sulfur. So structurally, they will have two thermodynamic.
Is it a covalent bonding? Because already the sulfur bond is saturated, so our hydrogen is again sitting there. Is it a absorption or it is a permanent covalent bonding?
No, there is no permanent covalent bonding actually, covalent bonding. This is just phase absorption. So there will charge transfer there.
Okay, we can discuss.
Yeah, sure.
Thank Akash for this nice talk.
Yeah, thanks.